7A, types of symmetry. So we're going to talk about on a graph, on a Cartesian plane, where you've got your x-axis and y-axis, how do we have parts of symmetry? Who knows what line symmetry talks about? Exactly. Think of it as a mirror. When you look in a mirror, that's symmetry. Okay, so symmetry means there's a mirror image. Okay, so something is symmetrical means if you cut it in half, it's going to be identical on both sides. Okay, that's what symmetry is. Okay, all right. So we're going to be talking about whether shapes, translations. Translations are talking about sliding images. Okay, so translations are slides. We talk about line symmetry, where we chop it in half if there's something reflected. And then we talk about rotational symmetry. And then we find out some objects have both. Some objects only have one of them, but some have both. Okay? So we're going to talk about that. Let's take a look. The first one's called line symmetry. So the first thing we know is line symmetry can be vertical or horizontal or slanted, which is our oblique. Okay? So what that means is, if I cut something in half, I can do it up and down, vertical, across, it's horizontal, or I can do it diagonally. That's cutting things in half. Okay? Just like we saw in the last one, which ones had symmetry, okay, and which ones have other symmetries. We have the letter H, the letter Z. Remember those ones last time? If you cut them in half, they're identically the same. Okay? And if you rotated them, they were the same. So some have rotational symmetry and line symmetry. So right here, I've got an object over here. If I say I want the mirror image, what am I actually doing? I'm copying it. So if it's going to be identical, what are you actually going to do to it? Yeah, you're going to reverse it and trace it over. Yeah. You're going to flip it. That's the word I'm looking for. So you're going to flip it over the line. Okay, because reflecting means you're flipping it over a line. Now, a good strategy, if you really want to, you can use your parchment paper and trace the object on parchment paper. Or you can take your best guess right now and try to draw it on your own. Okay, and if you draw like me, I don't recommend it. Ooh, I did pretty good, actually. A little more glitter. There's some eyes. There. That's as good as she gets in my world. All right, you might want to actually use the line and flip it over. Now, a lot of people will take their paper when they're doing symmetrical objects, and they will actually cut it along the line, use the dots, and push through the paper and put the edges of all the vertices. So you might want to push the paper through on each vertice. And if you push it through on the vertices, then you'll know, and then maybe draw this part really, really dark, and then flip it back over, you'll have that indented on the other side that you'll be able to trace. Okay? And that works as well. Okay? So, line symmetry happens when a line divides it into two equal reflected parts. That's also important. Two equal reflected parts. Okay? It's also called the line of reflection or an axis of symmetry. That's what it's also called. So it may have more than one line of symmetry. It can have multiples where it can flip over and be identical on both sides. And it may have none. It can also have none. So let's take a single line. If you had to do a line through this guy right here on the right, the top right, how could I cut this one in half so it would be identical as the other one? Or can I? What can I do to that one right there? I'm talking about this object right here. Can you go diagonal? All right, which way should I go diagonal? Should I go this way? Which way?
The other way, the exact opposite.
That way?
No, that's not the opposite way.
That way?
Yeah. No. Well, I mean, you would need a straight.
Well, yes, you need to make a straight edge, right? So, we're going to do this. You got to find out where exactly, like you said, it is going to be symmetrical. So, if you copy this line down straight and have a straight edge, and you flip that over the line, it should be symmetrical. Okay? That could be a line of symmetry for it. Does that have two identical shapes on either side now? You bet it does. So that guy is flipped over. He's got identical shapes on both sides. How about the letter E? So it says we've got a line of symmetry here. It's already cut it down this way. It wants you to draw the other one like it did the face. So if we have to draw the other guy, we're going to have to, oh, I really do not draw well at this.
Just flip it.
Yeah, just draw all the way down. Draw an E. Yeah.
Draw backwards, D, hey? There you go. Something like that. Hopefully you draw better than I do. Yeah.
The E on the right thing.
Does it have to be able to like match up?
Yes, on both sides.
Wouldn't the oblique one not match if I flipped it?
Right, that's only if it's a line of reflection. Here, the line of symmetry just wants it to cut it into two equal parts. Okay? If it's saying it's a reflected line, then yes, it's got to cover over top. Okay? All right, let's take a look at the next one. Where can we split these ones where it's going to be an exact copy?
Right down the middle of this.
Right down the middle of this one, okay? Let's draw a line right down the middle of that one. You're absolutely right. What about, now is there another way I can cut that one, or is there only one line of symmetry there? There's only one line of symmetry. Okay? Now, just like we saw it over here, if we go back to this question here, a good comment was, yes, I could cut it here and it's got two identical shapes, but are they reflected shapes?
No.
No, because if I actually flip that sucker over on that line, is it going to match up identically on top of him?
No.
No, it won't. So, would I say this one is actually a line of symmetry? No. We can divide it into two equal parts, but the point is, it's got to be reflected parts. Reflected parts mean you've got to chop it in half and it has to cover or coincide with itself identically. It's got to cover it.
It doesn't really have a
If we say this is the line of symmetry, then that would be a reflection line.
yeah, but it doesn't have.
You're right. So we would say no, there is none.
So then why would they put that on?
Because remember, they might have more or they may have none. They're showing us that some have none. Okay? So back to this question. If we have the object the x, how can I draw that x?
The lines, like to cut in half. Are you
Yeah.
asking? Oh, down the middle,
Down the middle, perfect, thank you.
down the side.
Where
through
what
the
side?
Through this
Horizontal through the middle?
and diagonal both sides.
You're absolutely right. So I can go diagonal through there and diagonal through there. So how many do I have in that one?
4.
4. This one's got 4 reflection lines, 4 lines of symmetry. This one only had 1 line of symmetry, which is called a reflection line. What about the bottom? It looks kind of like a barbell weight. That's the back.
Straight down the middle
Straight down the middle.
and side.
Right through the middle sideways, absolutely.
Oh,
Can I go diagonal on this one?
yes, you can.
Yeah.
Yes, you can. Yes, you can. No, you can.
Okay.
Yeah.
I'm going to challenge you.
If you cross the center, it can be.
I'm going to challenge you. Take one of your pieces of parchment paper and try to do it diagonal. Now remember, if it's diagonal, it would have to go through the middle. So you're going to be doing it this way and see if from this corner to this corner, if it works. Yeah, you're right, it doesn't. It's only got 2 lines of symmetry. It will not. Diagonal, it doesn't. Try it. It'll prove to you it won't.
If it's a reflection, though, it's the same.
It won't work this way. I will show you. I will prove to you that diagonally it won't work. Okay, on this question. This is called a regular polygon. Regular polygons have every side the same length. So it would be like an equilateral triangle. All sides are the same. It would be like a square. All sides are the same. Okay? A diamond. All sides are the same. If there's a pentagon or a hexagon, that means that all sides are the same. If it's called, this word, a regular polygon. Okay? Now, if it's a regular polygon, they've got the same number of reflection lines as it does corner points, called vertices. So if you count the vertices, I've got 1, 2, 3, 4, 5 on my pentagon. I have 5 vertices, which means I can cut that guy in half 5 times, 5 different ways. So if I go right down the middle, I can cut it in the middle and it'll flip over top and cover exactly. If I go this way and cut through, it's going to be the exact same thing. And you're going to go through each one of them and they're going to form, they're all going to meet in the middle. That guy will have 5. This guy will have 6. How many should he have? 4. How many should the square have? 4. How many should this guy have? Well, we're going to pretend it to be equilateral. I know it's not, but we're going to pretend it is. We're going to put these ticks on to say it is. So here we have 3. What about a star? Does that follow our rules? Yeah, it does. If you cut it this way, there's 1. If I cut it this way, there's 2. I can cut it this way, there's 3. This way, there's 4. That way, there's 5. It will work every time. Okay, because it's a regular polygon. Okay? Let's take a look at what these mean. So, it says it's going to divide it into 2 congruent parts. What did we learn the word congruent meant? What does congruent mean? Brett should know because he is one. It's a twin. It's an identical twin. Okay? So identical twins are congruent. So congruent means the same in every way. Now I know as they grow up they change, but they're supposed to be identical twins. So in this one, I'm going to show all of my lines. Now, there's one line, vertical. But what if I join these ones, B to E? Is that a reflection line?
No.
No. How come? Exactly. If you fold it in half, it doesn't cover itself exactly the same. There's still parts of it sticking out. You have to cover it exactly identical if it's going to be a reflection. Okay? So, where they should have drawn is from here through and cutting the other side. From a vertice to cut the other side. From a vertice to cut the other side. Vertice, cut the other side, and a vertice to cut the other side. And they will all meet in the middle always. Okay? So again, this guy being a pentagon will have 5. Now we're going to start to talk about rotational symmetry. Pardon, it's all right? Yes, if it's a regular polygon, it would be. But this guy, well, again, I didn't draw it right when I drew it. And it's supposed to be a regular polygon. But just like the triangle, I didn't draw it very well. But these are considered regular polygons, is what we're talking about. Okay, here is rotational symmetry. So now we talked about rotational symmetry already a little bit. It's when a shape or design hovers or turns around the center so that it's going to fit onto its outline, which means covering itself or coinciding with itself. That all means the same thing. More than once. That's important. More than once in one term. Because what happens if you get a rotational order of 1? Does it actually have one? No, because every object has a rotational order of 1. You can always turn an object around and get back to its same spot. Okay? Every object has that. That's why it's not considered a rotational order. You have to have a number larger than 1, and the degrees have to be how far? Less than 360. Good. Okay, so they have rotation point centers, and that's where you actually turn the object. That's where you're going to write your plus sign on the parchment paper and turn it. Okay? That's what we did this morning. Now remember, your rotation point, like we saw this morning, could be a corner, a vertex, but it could also be the center of the object. Okay? It could be right in the middle of the object. It also could be the 0, 0 origin on a Cartesian plane. So it can rotate from a number of different parts. Then we have rotational order. Again, that's the number of times it fits onto itself in one turn. And then we also have the rotational angle. And that's how far it turns each turn. So, let's take a look at the next examples. What would the rotational order of that be? What is the rotational order of that flag? Yep. 2? Are we in agreement? Is it 2? Yeah, you're right. So, if it's 2, that means that you're putting your parchment paper on it, you're putting a little dot and the plus sign in the middle, and you're going to rotate it. How many times is it going to turn and cover itself completely? It'll do it twice. So, if our rotational order is 2, how do we find out our angle, how far it moved each turn? What do I have to do to the numbers?
Divide
By what?
360.
You're on the right track, but you're a little mixed up. Good. 360 degrees divided by 2 means each turn is 180. So each time it turns and covers itself is 180 degrees. It won't do it in 90, it won't do it in 75, and it won't do it in 50. It has to go a full 180 before it covers itself. Okay? Rotational angle as a fraction. Well, if I want to leave it as a fraction, I would just make this go in the lowest terms. So it would be 180. How do you make any number into a fraction? Over 1. Yes. What about this guy? What would his order of rotation be? What do you think? It is 3. Yeah, absolutely it's 3. Okay, and if you're not sure, grab your parchment paper and put it on. Okay? Angle of rotation. 360 divided by 3 is how far? 120 degrees. So it went 120 over 1. Okay? What is the order of rotation of this guy? And it always will be for these situations. What should it be? 5. Good. It's going to be 5. Because it's like the star we did. You cut this guy here, cut it here, cut it here, and cut it here, and here. Those are lines of symmetry, which means you can rotate it that many times as well where it covers itself. Okay? So this object here would have line symmetry and rotational symmetry. So we would say 5. Now we get 360 divided by 5. What's our rotational angle? 72 degrees. So we, as a fraction, we would say 72 over 1. Okay? Now, a lot of people might read the fraction like this. Do we ever read fractions that are not reduced? No, we don't. We always reduce our fractions. All right. Almost done our reflecting, or rotating. Next one. We're going to translate some stuff. Well, translating means translate or slide. That's what translate means. It means slide each of the vertices, so each of the points, forward to the right. Well, that means all I do is I take this object and I count 4 to the right. And that's where I make the new point. So, 1, 2, 3, 4. I'm going to make my new point. There's R prime. I take the T, I count 4 over, darn it, guess who he's sitting on top of? He's sitting on top of S, he's partying with S, oh boy. Now I'm going to move S forward to the right. S ends up over here, S prime, there's T prime. And I join my points. Alright. Now, what order pair represents the first set? So RST is our original, RS and T. So we need to find out their location on a map is what it's saying. What is the ordered pair? Ordered pair means the X number and Y number of its location. Okay? That means X comma Y. What is the location on this grid? So you're going to see how far left did it go and how far up did it go. So this guy went from here all the way left and then up 1. How far did he go? How many steps did he go left? 7. So that's letter T, pardon me. Letter T went 7 left, which is negatives. He ended up in the negatives. And he went 1 up. So that's his point. That's where he ended up. The S, what about S? What is our point for S? Where is he located right there? He went 3 right and how far? 1 up. So, -3, 1. And then we've got R sitting over here. How far did R go? So R went 1, 2, 3, 4, 5 steps, and then up how far? I don't know if I did it right. Okay, there we go. Negative 5, 5. So now we've got the actual locations on the map for that guy. Now we want to say, what are the new locations of our new points? Well, what did we know about T? T prime became what letter? T prime became S. So we can put S prime on for sure. Or sorry, we can put T prime. T prime is the same as our S up here. So he's at negative 3, 1. What do you notice they did to the numbers? What do you think? What happened to T? If you look at T, negative 7, negative 3. What happened to the numbers? These numbers didn't change, but these numbers changed. What happened to the numbers? They added 4. Well, they added 4, and what did it tell me to do? 4 to the right. So if I'm moving right, am I adding or subtracting? I'm adding. So 4 units to the right means take your X number and add 4. So now I don't even have to look at the numbers on the map. I can take S and I can take R and I can add 4 to those X numbers and get their new numbers. So if I take S, what's negative 3 plus 4? 1. And the 1 doesn't change over here. Where did he end up? At 1, 1. Okay? Let's take R. If I add 4 to the negative 5, where do I end up? Negative 1, comma, 5. What do you know about this guy? Where did he end up? Negative 1 and 5. Now, how do I know those numbers exist and that's where they are? It's because we always start at 0, 0 in the middle there. Just like we do with our graphing unit for linear relations. We always start at 0, 0 in the middle. And then we find our point from there. Okay. Now, if I look at that image, does it contain rotational symmetry? Can I rotate that and make it sit on top of itself? Is that possible?
Well, the image.
Okay, good. The new image. Okay, the new image. Does it contain rotational symmetry? No. But, does it have line symmetry? Can you cut that sucker in half and have an identical object on both sides? Yeah, you can. So, we're going to say there's no rotational symmetry. Okay? Because there's no point that it can be rotated around where it's going to coincide. Coincide means sit on top of itself. Okay? But is it symmetrical about a line? Yes. Now, which line is that? If I draw this line on here, the line would go right there, correct? Well, how do I write a vertical line as an equation? How do I write a vertical line? What is it always going to start with? What letter? What letter is it touching down here? X. It's going to be an X equal line. Okay, X equals what? Now, what number is he? 1, 2, 3 to the left. What's 3 to the left? Negative 3. So, what it says for image being symmetrical about a line, that means it looks at that X negative 3 line and says, I'm going to jump over you. And it flips over that negative 3 line. Boom. And line's there. Okay? And that's what it's talking about. Does that make sense? Pretty good so far? Alright, let's try it with this one. Try this question. It says it wants it to go 3 right and 3 down. Move each of those points 3 right and 3 down and write your points here, please. I'll give you a couple minutes to do that, just like we did with the other question. Okay, so draw your new object. You should have got that by moving every point 3 to the right and 3 down. Okay, 3 right, 3 down, 3 right, 3 down for each of those. Now we need to write the coordinates of where it's sitting. Where's that object sitting now? Well, if we know that's 0, 0, but we're telling us we're moving right 3, right means we add to x. So if I take all of these x numbers right here, I'm going to add 3. That's going to give us my new x numbers. So negative 7 plusing 3, what do I get? Negative 4. What's negative 5 plusing 3? Negative 2. What's negative 9 plusing 3? Negative 6. Excellent. Now we're going to do the other one. We're going to do the same thing, but now these guys are telling us we're going down 3. Down means we subtract. So if I take negative 2 and I'm on the number line at negative 2, I'm going to subtract 3 more. Where do I end up? Negative 5. If I'm at negative 6 on the number line and I'm going to take off and go 5 more left, where do I end up? Or 3 more, pardon me. Negative 9. Okay, check your work. Did you get all those points correct? Excellent. Now, what kind of symmetry does it have? Does it have rotational or line symmetry? Either of them? Can I rotate it? No rotational symmetry, no line symmetry. There's neither. So if you said nope, none of the above, you are right. It doesn't have either of them. Okay? Now, if you want to get real specific and understand why, the reason is this.
Translate.
Because there's no point about which means where it can rotate so that it touches and coincides, meaning covers itself exactly. There's no point where it'll do that. If you try any point, it won't work on these ones. And this one, there's no line where you can chop it in half to produce a mirror image. It won't do it. Okay? That's the reasons why. You can't make a mirror image, and you can't turn it from somewhere to make it copy itself. Okay? And sit on top of itself. It won't do it. Let's take the next one. Now, this one says we're going to reflect. Well, what's another word for reflect that we talked about? Somebody said it earlier. Flip it. We're going to flip it. Reflect means flip. Well, if it says we're going to flip it in the x-axis, that means I'm taking this line and I'm going to take the object and flip it down. Okay? I'm flipping it down. So, that means it's going to come here. I have 3 spaces here. How you reflect is you count how many spaces away from your reflection line the point is. And then you go the opposite way across. So, point D is right on the reflection line. So is it going to change spots? No. Point C is right on the reflection line. Does it change spots? Nope. But A is 3 spaces away. So I need to go 3 spaces away to make A prime. B is also 3 spaces away. So I need to go 3 spaces away the other way. And there's B prime. Now I connect my dots. And now I've got my new object. It's flipped downwards. Now, for my objects, if I do this and I write my points we have here. You had a couple minutes here. Let's figure out what the points are. So where did A, what's our original point for A? Where's A at? Negative 2, positive 3, good. Where is B?
4, 3.
4 and positive 3, excellent. Now where do they end up when we flip them? Where does A prime end up? Negative 2, and then it goes down, how many spaces? Negative 3, good. Where does B prime end up? Positive 4 and negative 3, goes 3 down. Okay? All right, now we're going to check and see, does it have rotational symmetry? So, hang on, that's not what I wanted to show you. Rotational symmetry. Yes, it does. We can rotate that guy as long as we rotate it around the middle. What is the middle of this object? Well, if we take a look, the middle of this object is right there. Okay, that's the middle of our object. So that middle of our object is at what point? 1 and 0. So that's what it's saying. About the point 1, 0, that means that's going to be the middle of the object. Can it rotate? Yes, it can, around that object, around that point. Okay, so this is that middle point it can rotate around. Then it's going to say, well, our new object, the newly formed object, does it have line symmetry? Well, what did I form? I formed a square. Now, if it's an exact square, we know we can cut it how many times? 4, because it's got how many vertices? 4. So I can cut it through the middle, left and right, of course. I can go diagonal, and then I can go corner to corner this way. Okay? So we can do it, and it's going to look a lot like this one. Grab him and bring him over. It's going to look like that. Okay? So there's 2 9s. There's the other 2 9s. So it's got 4 9s. Let's move him back. So, is there symmetry in the new one? Yes, there is symmetry, but it's saying line symmetry. Can I flip it over a line? That is an incorrect answer. Yes, you can.
You went to number 4. An example.
Oh, I'm on example 4. I'm on the wrong one, aren't I? There's my question. This one. Yes. It's got lots of lines of symmetry. As we know, I can reflect it vertically over this point. I can reflect it on the horizontal x-axis, and I can reflect it diagonally on both of those. That's what this is telling us. So if we go up here, it's saying we have 4 lines of symmetry, which we have drawn. Please write out what those lines of symmetry are. Write this out now, please. Next example. Again, we're starting with the same one. We have the exact same answer here for our points. And then it's going to say we want to go 180. Okay? From the middle. If I go 180 from this middle right here, where's my object going to end up? Give that a try. Rotate that 180 degrees. Use your parchment paper and rotate that sucker. Where does he end up? So, here's the confusion. Many might think that it's got rotational symmetry. But, I rotated it 180 degrees. Is it sitting on top of itself here? No. So that means there's no rotational symmetry. If I rotated it 180 again, would it sit on top of itself? Yes. But that means it rotated and sat on top of itself in exactly one turn of 360. When it does it in one turn, we say it's got no rotational symmetry. It has to be less than.
But it's asking for both of them together.
Yes. Oh, wait a minute.
Maybe we did.
The new one? This one's talking about the line symmetry of the newly formed angle. Oh yeah, this one is too. No, this one's just talking rotational symmetry. Is just saying this object, if you rotate it around, is it going to sit on top of itself?
But it's not referring to that object, it's referring to the whole thing.
Rotational symmetry, it's still not going to sit on top of itself if you rotate it from the middle. It still won't, in less than one turn. If I turn it 180 it's going to be here upside down. It's not going to turn and sit on top of itself.
If both of them turn.
They have to, and they're only going to turn and do it in 360. They won't do it in 180, they'll do it in 360. Because if I do it in 180, it's going to end up like this. One's going to end up over here, and one's going to end up over here. Try it with a parchment paper. Give it a try. Okay, try that with a parchment paper. This is the next one to try.
You can't do it.
Sorry, which one, dear? Let's just see here. It says go 6 to the right, 3 down. Oh, we ran out of room, don't we? Okay, well that's just fine. All I want you to know is, are you able to take 6 and since it's going to the right, can you add 6 to each x? That's what it's basically understanding the concept is what it wants you to do. On this one, 3 down, you need to subtract 3 to your y's. It's that same concept. It wants you to know, can you do that to the object? Okay? When you do, the object is going to look down here. It's going to be like this. Like that. It's going to sit over there. Okay? That's where it's going to sit. So just draw a couple points. It's going to have a couple points just off the side here. That's where it's going to be. Okay? Now, is there line symmetry? Can I put a line through it? What do you think? If I cut it in half down here, right down this, if I cut it in half and have it flip on top of itself, this guy goes here, this guy goes here. They're not touching each other or covering on top of itself. Okay? So it's got no line symmetry. Okay? But if I want to rotate it, as long as I rotate around point C, definitely I can rotate it. Okay? Next example. What happened to those two? Are they related by symmetry? So, is there a rotating point I can put it on where it'll rotate and cover itself? Yeah.
0, -4.
Right there, yeah. Absolutely. It's exactly where you'll rotate it from. Okay? So if you go right here and you rotate that and put it on your parchment paper, it's going to go again, 180, 180. So it's going to be a rotation order of 2, 180 degrees both ways.
The one previously does have rotational symmetry.
Did you prove it? It did?
Yeah.
Okay, so that answer was wrong then? Okay. So that back one that he's talking about, is that this one there, dear?
Yeah.
Yes? Okay. So this is incorrect. We would say yes, it does. Now, does it rotate twice? Is it 180?
Yeah.
Okay, so it's 180 then. Okay, so it's going to do twice. 2 times it will. Okay, so thank you for correcting that for us. Okay, this one back to this guy. No line symmetry. This one, is there line symmetry in this one? If I cut this guy in half any which way, what about diagonal? If I go diagonal, would it work?
Yes.
Are you sure? This guy's going to flip upwards. He's going to be pointing this way. Is it going to cover this one? No, it's not going to. So this one's going to have no line symmetry. Okay, so it's basically yes and no's. What about that one? Holy cow. Can I flip the top one down onto the bottom one? Yes. So there is line symmetry. I can flip it over that line right there. How do I know? And how do you know what the line's going to be? You count the spaces between the objects. This object has 6 spaces between. Divide it by 2. So that you go 3 spaces up or 3 spaces down, that's the line that's going to flip over. Okay? Now, can it rotate anywhere? Yeah.
So does it have to be an even number, like divide, like
No.
have to be an even
No,
number?
it could have been 7 divided by 2, it could be something and a half. It could be a 0.5, absolutely. And that's going to happen with this one.
Does there have to be an equal amount on each side, like equal to each other?
Yes, yes. So that means if this guy was lower or whatever, it might be down here. Okay, yes. Okay, what about rotation symmetry? So we know we said yes for line symmetry. What about rotational symmetry? Yes, it's got both. Okay, so just say yes, yes, it has both.
How does rotational symmetry work?
Okay, last 2 examples. Look at the new object. How is this one related? It's like that plus sign we saw before. Count the vertices. So, I can cut it this way, diagonal, diagonal. How many ways can I cut it?
Multiple ways.
4, multiple ways. Line symmetry, yes, there's 4.
Why wouldn't it be?
Yeah, there's extra vertices, but you can't take it from this vertice to this vertice down here and have it flip directly on top. Okay?
Right, so then.
You gotta take it through the middle, like a pentagon.
Yeah, as long as the.
Yes. It's if there's exact points. If it's, okay, a polygon is going to have, a regular polygon has points that are all pointing outwards, and there's nothing pointing inwards. This has pointing inwards points, so we can't go by that. The star, same reason, but the star, because it had no other things inside it, it only had them coming in, we could use it.
Wait.
Right, and there was 5 of them though, and it worked. This one, it would work, but it only works for each one of these. This is like the star having a point, it works for each one of those. But these aren't pointed. The star just has points here, right? That's what it's like. These guys just don't have points. Okay? Last question, yes, it has rotational symmetry, and yes, it has line symmetry. This concludes lesson 6.7a, types of symmetry. Yo,